afternoon once again. Welcome back to the third part of our lesson today, which we call the angular velocity 3. Now, today's lesson will look into another dimension in which we can actually find the relationship between the angular velocity and the linear velocity. So quickly, take a look at these two diagrams on the board. I've got this particular diagram. Let's take, for example, I've got a stone that is tied at the end of a rope. Now, this stone tied to the end of the rope is basically whirled round to form a circular motion. Now, if you take this point O as the center, and you take P as you take OP as the radius, now the OP will move over this particular distance, which we call S, which is kind of a displacement, and it will land in OQ. Now, if you look at the velocity, you can actually see that the velocity is tangential. Basically, it is changing due to the changing displacement that is going on there. Now, this is another diagram that is exactly like the one we have here, but we're looking directly, this one we're looking directly from the top. This one we have another view completely. So in this case as well, you can see the angle theta, you can see the radius, you can see OP, and you can see OQ, then you can see S, giving us the displacement, then we have V, the velocity. Now, let's quickly analyze what is going on here. Now, if I have OP, you can actually see that the angle theta is moving through angle P and Q over time T. That is, there is a kind of displacement. This angle theta is rotating between P to Q. That's the kind of movement it has over a particular period of time. Now, what else is going on here? Also, if you look at the radius OP, the radius OP is moving from this point OP over the displacement into OQ. OP to OQ, the radius is moving over the same time. So the radius moves over the same time. Now, so what do we need to deduct from here? Remember, in the initial lessons, or in the previous lessons we had, we discussed about angular velocity, and we said angular velocity, based on what is here, equals to, let's quickly put it here, angular velocity, which is omega, equals to theta, in this case, theta over time, over the time it is moving from one point to the other. So I have this. This is the equation that results from what we have due to the movement of the stone in a circular path. So this is basically the displacement path. This is the angle of displacement that we have here over a particular period of time. Now, let us move on further. We were told in the previous lesson that radian, that is 2 pi radian, has to do with the revolution in terms of moving in the circular path. And this revolution in the circular path is also equal to 360 degrees. So 2 pi radian completes a revolution, and the revolution of 2 pi radian will give us an angle of 360 degrees. Now, theta is measured in radian. Okay, so we have, in this case, this will become radian per second. So it takes us back again to what we did earlier. whereby angular velocity equals to 2 pi radian per second, if you remember clearly. Now, we're not done here. If you look at what is going on here, there's a displacement between P and Q. Now, this displacement can be summed up as well by using a particular equation we're familiar with. Let me take your mind to that equation. If you remember linear velocity. Now, in linear velocity, we have velocity equals to S over T. Now, in this case, my S is my displacement. Okay, now, if you look at this equation properly, there is a similarity. We call this the linear velocity. We call this the angular. Let me actually put it there. This is called the angular. So, angular velocity. Then, don't forget, this one is called the linear velocity. Yeah, so that you can remember. Don't forget the S that we have here, which is similar to this one, is called the displacement. Now, in this case now, the displacement here, which is equal to this angle we have here, we call this the angular displacement. This is our angular displacement. Now, this one basically, because it's on the linear velocity, this one will be our linear displacement. Okay. Now, looking at what is going on out here and what is going on in here, we can actually forge an equation out of what is actually happening here. So how do we forge an equation in what is happening here? I think I will have to actually rub off a part of the board. Let me try and rub this section off completely. Now, the next thing we now need to do is to bring them together. How do we bring them together? We have omega equals to theta over t. But if you remember, I told you also as the angle omega equals to theta over t, as the angle is moving from P to Q, it is moving through a displacement S. So we have a displacement S is also equal to, we can also say theta, let's put it this way, theta is also equal to this displacement S over time. So in this case we have the R, the radius moving from one point to the other, so we have R there. So we can see there's a relationship between these angular displacement being equal to the displacement S that is going on here over a particular time. Now, let us see the comparisons that are here. Now, what we now need to do is to basically look into this. So this becomes S equals to theta R. That is another equation that we can deduct from here. But that is not where we're going. We realize that omega, let me see, do I have enough space? I'm going to use this section. So we realize that omega equals to theta over t. Now, what is theta? Theta is S over R over t. Now, just watch what is going to happen. Now, we have omega equals to, let's break this down. So this becomes S over R over t multiplied by 1 over R. So in this case now, we have, let's quickly see what we have here. So we have this becoming omega equals to V dot 1 over R. Now this now becomes omega R equals to V. As you can see again, we're back to the same equation. Linear velocity equals to basically a relationship in angular velocity. Thank you very much and have a nice day.